All right, hi folks, this is Larry Mussolino. I wanted to record a video for Module 2 here in Math 230. So Module 2 is all about proofs. And so as you work through this module, you're going to be looking at different proofs. And one way is a proof by a method called contrapositive. Then there's a method called contradiction. There's a method called induction and so on. Here's a suggestion for each one of these methods. Make a one-page summary for yourself where you list out the steps, and then maybe think of it as a table with two columns. On the left side, list out the steps to follow in general. And on the right side of this table, come up with a specific example where you show yourself how you implement that step in an actual example. This way, when you go back and look at this later, you have a nice reference sheet to look at to remind you of these different methods. So let me give you a quick example here of working with contrapositive, because a few students were asking me about that, and it's a little tricky until you see the setup. So let's take a look at it. Let me click here on proof by contrapositive. And so it says for proof by contrapositive, you're going to be looking at some kind of a theorem that has if P, then C. So we write that with the arrow, right? So P implies C. How do you do that? Well, if you can show the contrapositive, what that means is you have to take not C and show that that implies not P. If you can show that's true, then you prove the theorem. Okay? And so what you're looking for is some kind of a hypothesis for if P, then C. P is like a proposition and C is the conclusion. Let's do an example. I think that's the best way to see that. Let's come here. And here is an example. It says, give a proof by contrapositive that for every integer n, if 3n plus 7 is odd, then n is even. So let me write it. If 3n plus 7 is odd, then n is an even number, even integer. Well, here is the P statement, and here is the C statement. So I want to, in order to prove this, I'm going to flip it around to prove this statement. What I'm going to do is show that, where is it? Right here. Not C implies not P. So let's apply to our example here. C was a statement n is even. So not C translates to the statement if n is odd. So if n is odd, then we need not P. Then 3n plus 7 is not odd. That must mean it's even. So we need to be able to show this statement, and that will prove the original theorem. And you might say, well, why do you do this? You still have to prove an if-then statement. Well, it turns out this statement is going to be easier to prove than the original statement, because you can start out with n being odd and then just prove that 3n plus 7 is odd, and you're done. All right, so let me scroll down a little bit, and I'll show you the details of this. Okay, and this is a little animation, so, okay. And so what they're trying to show you here is you're going to start out with this if-then statement. Okay. And they're going to tell you now you should take the negation of the conclusion. So here was the conclusion. I have to take the negation of that. Let's write it. So if not n is even, then we have to show the negation of the hypothesis. That would be the negation of 3n plus 7 is odd. Well, the negation of n being even, that's n being odd. So if n is odd, then the negation of 3n plus 7 being odd is 3n plus 7 is even. Okay? So here it is. We're going to negate the conclusion and derive the negation of the hypothesis. So the negation of the conclusion is n is an odd integer. Well, here's the key. If you think of n being an odd integer, then n is 2k plus 1, where k is any integer. So let's see if this makes sense. If k is any number, when you multiply it by 2, this is always going to be even. Think about it. Let's say k is 1, k is 2, k is 3, k is 4, k is 5, etc. Right? K is any integer. What about 2k? Well, that's going to be 2, 4, 6, 8, 10. Do you agree 2k is always going to be an even number? You could see it here. But let's form 2k plus 1. 2k plus 1, that's going to be 3, 5, 7, 9, 11. I could see 2k plus 1 then is going to be odd. All right, so now we have n equal 2k plus 1. We want to show that 3n plus 7 is even now. So take 3n plus 7 and replace it with the n with 2k plus 1, right? Because that's our statement here. N is 2k plus 1. So I'm going to write this as 3, 2k plus 1 plus 7. Let me scroll down and I'll show you this in more detail here. And so I guess I shouldn't have erased it, but here. So we're trying to show that 3n plus 7 is even. But we said we're going to let n be 2k plus 1 because we want n to be odd. And if n is odd, we can write n as 2k plus 1. So let's plug in here 3, 2k plus 1 plus 7. All right, let me just multiply the 3 inside the parentheses here. So this is going to be 6k plus 6 plus 13. All right, so this is going to be 6k plus 20. And what I could do now is I can factor out a 2 from this expression. So I'm going to factor out a 2. Now, why am I going to factor out a 2? Well, I'll explain in a second. Let me take a 2 out. That's going to leave me 3k plus 10. I'm sorry, this should have been a 10 here. Let me go back. I'm sorry, I made a little mistake here. Let me fix this. I made a mistake with some basic algebra. That's not good. But let me fix it. So 3 times 2k is 6k. 3 times 1 is 3. Bring down that plus 7. So this is going to be 6k plus 10. Now I'm going to factor a 2 out in front. That's going to leave me 3k plus 5. Now, why did I factor a 2 out in front? Because if I take 2 times any number, any integer here, it's going to be even, right? Because if you take 2 times a number, it automatically makes that result even. So I just showed that this is going to be even because it can be written as 2 times a quantity. That proves, we use the contrapositive then to prove the original hypothesis and conclusion. All right, let's do another example here. It says, for every positive integer x, if x to the third is even, then x is even. All right, let's say we want to prove this by using contrapositive. Well, think of this as P and think of this as C. All right, to prove this, we want to show the contrapositive. We want to show that not C implies not P. Well, not C is not X is even. And not P is not X to the third is even. Well, the negation of X being even is X is odd. And the negation of X to the third being even is X to the third is odd. So if we can prove this statement down here, we will have proved the original conclusion. All right. So what they're going to ask you to do is identify A, B, and C. So A is the original assumption. So it says assume A. So really this is A. And we want to prove B. I'm sorry, this is the contrapositive. I'm sorry, let me go back for a second. Get rid of this stuff. So they're asking us for the proof. We're going to assume A. So I think they mean here the contrapositive. So this is going to be A. And we want to prove B. This is going to be B. Okay. All right. So it says, what's the correct expression for A? Well, that was the negation of the original conclusion. So that's X is odd. So I'm going to click here, X is odd. What is the correct expression for B? Well, down here in the lower right, you can see X to the third is odd. What is the correct expression for C? Now, what do they mean when they say C? Well, notice here it says if X is odd, then it can be written in the form of C. Well, you remember if you have 2K, that's going to be an even integer. But if you work out 2K plus 1, that's going to be odd. So we want to be able to show that X is odd. So here is an expression that's going to turn out to be odd. So let me select that one. And then what's the correct expression for D? Well, by D, they mean X to the third. Let me go down to this bottom one. What is the best expression for E? And it says both choices are equivalent to X to the third, but one does a better job of showing that X to the third is odd. Well, if you notice, this first expression here is in the form 2K plus 1. And we know that implies an odd integer. So I'm going to select that answer choice for that. Okay. All right. Let's come down here. Let's do one more activity here. It says, below are the steps of a proof by contrapositive of this following theorem. It says if X to the third plus 2X plus 1 is less than or equal to 0, then X is less than or equal to 0. And it says X is a real number. That means X could be a decimal number or a whole number. All right, well, this is P, and this is C. We want to be able to show the contrapositive, which is not C, implies not P. Not C would be not that X is less than or equal to 0. Not P would be not X to the third plus 2X plus 1 is less than or equal to 0. Well, the negation of X being less than or equal to 0 flips it to be X greater than 0. And the negation back here is going to be X to the third plus 2X plus 1 is greater than 0. So that's the outline of the proof. All right, let's go ahead and drag these blue tiles into the right order. All right. I think the first one we're going to need is this assumption that x is greater than 0, right? Because notice down here, let me circle this in purple so you can see it. Here is our assumption, x is greater than 0. So that's a good starting place. So let me drag that here. Okay. All right, now we want to be able to show that this is our conclusion back here. So I can see the conclusion is going to be this statement. So I'm going to drag that down to step 4 because I can see that's kind of the last concluding statement. All right. I think the next statement we should use is this statement here that says if x is greater than 0, then the different components, like 2x, that's greater than 0. X to the third is greater than 0. And our third statement here is this one that says, since all the pieces are greater than 0, their sum also has to be greater than 0. Okay, so that kind of makes a logical sequence of the proof here. And again, this is called proof by contrapositive. All right, folks, hope that's helpful as you're working in this section 2.6.